In the program, 4 works that will be presented. The first presenter is the author of the work titled Click Event Sound Detection Using Machine Learning in Automotive Industry. All the attendees can write any question in the chat, and at the end of the presentation, I will translate these questions to our first speaker. So please, Luney Hernandez, you will present, that's right?
Yes, it's correct.
Okay, go ahead. Please share your screen and start when you are ready.
Thank you. Can you see the screen correctly?
Yes, it looks very good.
Okay, thank you. So, hello and welcome. I'm going to present to you click event sound detection using machine learning in the automobile industry, where Ricardo Espinosa, Irán Ponce, Sebastián Gutiérrez, and I, a student of artificial intelligence engineering at Universidad Panamericana, collaborated. So, let's start with this section. Sound classification and natural language processing. Why are they so important? So nowadays, information or data has been extremely used to understand human activities and even nature events. One of the most common and distinguishable things for us is to have the ability to understand sounds, their characteristics and origin. Natural language processing, as we know, enables us to understand those events in a more technical way, developing our knowledge and understanding of sound and human speech, including emotions and language structure. Natural language processing has some topics in its regard that are widely used in the industry today, such as named entity recognition, tokenization, sentiment analysis, natural language generation, and in this case, sound classification or recognition. So what did we do? Well, various classification and detection studies have been proposed through techniques for sound detection that have been able to classify audio signals under experimental noise conditions with the use of deep learning. There is very few information available in the literature in diagnosing car engine failures using a detection system and machine learning. Why? Well, it's because sound recognition systems have been mostly focused on speech and musical signals. However, event sound recognition systems have received more debate or attention in recent years. Traditional machine learning techniques have been characterized for their reliability and acoustic event detection to improve the detection events. So, introducing the problem, we're seeking to improve the quality of assemblies in the automobile industry. Since the arrival of the Industry 4.0, the automation of assemblies in a production line has been subject to change and continuous improvement. And the way we seek to improve this is by utilizing artificial intelligence, by using some techniques that are known for having their own applications within machine learning. After trying, we perceived that not everything, or the main challenge was that not everything can be automated in an assembly line. And this happens because there's not enough space for big machines or even little ones that could connect 6 harnesses. And therefore, this task can only be performed by humans. But this implies a risk factor for employees as well. We can see that there's also a noisy background in the assembly line production. So talking about the state of the art, the literature addresses a real method to picture data identified with assembly and quality in the creation of cars, permitting the control of imperfection data in a manner arranged to the working and assembly line to work perfectly. And there's been a lot of classification detection studies recently. And for example, there's been whale species classification based on their whistles, classification of emotions and needs of newborn babies, of common sounds, classification of shootings inside human environments and illegal forest activities. Some few authors have worked with engines and machine learning techniques. In this case, for example, some researchers presented machine learning techniques of auto samples to detect an engine failure. And one of the most remarkable ones was when the researchers formed an intelligent diagnostic framework, allowing to determine both single and simultaneous faults for CAN engines. So why is this research so important? So we're presenting an application developed and testing to a manufacturing enterprise, being able to detect appropriate assembly from harnesses connections using a multi-layer perceptron. And this was implemented and tested to detect click event sounds within a real assembly production line. And as far as we are aware, this is the first time in which machine learning is applied to sound detection events of harnesses with the objective of improving the quality of manufacturing in the automotive industry. So this is our proposal. First, we will have the data collection. Then we will proceed to have the pre-processing of these data with these algorithms. Then we will extract the features that are mentioned in this. And then we will classify with a classical machine learning model to obtain the result of a good or not good assembly. So starting with the first section, data collection, we stored the sounds of 6 harness connections, and the sounds were recorded with a microphone that was placed 35 centimeters above the workstation. And thus, the dataset was composed by 25,000 samples that were recorded through 3 months of production with 0.025 seconds windows of duration, with class 0 indicating that there was no click, and a class 1 indicating that there was a click. So we chose 0.025 seconds for our click window sound as a period of time, since we extracted the average time that the click event taking all the collected data. And this data discriminates frequencies greater than 10 kilohertz that are the surrounding sounds or noise of the click sound events. And since the microphone was able to record only up to 22 kilohertz, we can perceive that in the picture, and where the max frequencies are able to reach that point. So starting with pre-processing, we use noise reduction, pre-emphasis filter, and an onset detection algorithm. So we chose these techniques because recording the assembly production line sounds involves background noise. So we implemented pre-processing in dimension 3 steps. And in this particular work, we added a separate detection phase from the original methodology of the collected audio to then continue with feature extraction, which can be later used with the finality of improving data analysis and finding ideal features. So proceeding with noise reduction, we had spectral gating. So depending on real noise of every audio clip, noise gates are used by spectral gating-based noise reduction technique in the Fourier domain to separate reasonable image structure from background noise using the statistics of local neighborhoods in the signal. After that, we store the first 0.5 seconds of each audio clip. As you can see in the image, after implementing this step, we can determine that there was some noise that was removed from the sound. So after that, we have a pre-emphasis filter, which will amplify higher frequencies of the signal or the noise reduced audio signal. And this step is very useful in several ways. The frequency spectrum gets balanced. And since higher frequencies usually have smaller magnitudes compared to lower frequencies, it will avoid numerical problems throughout the Fourier transformation operation. And this will improve signal to noise ratio. And we can see in the formula that the signal is represented as x, the time will be t, and the filter coefficient will be alpha, and the result will be y in t. So after applying this step, we can see that high frequencies are amplified. And the onset detection algorithm, which uses a spectral flux algorithm based on maximal filter or vibrato suppression technique, will detect, frequency changes by peaks in an onset strength envelope in frequencies between 10 kilohertz and 22 kilohertz. And these time steps allow detection of sound click events locations. And we extracted windows of 0.025 seconds, subtracting 1,024 samples from the collected filter audio by the spectral flux algorithm. And this will be later processed by feature extraction. So we can see the full process here of the pre-processing, where we can see that our data is now enriched in a way that we can better work with it. And once we start extracting with our features, and we can see in the onset detection algorithm that we also segmented the onsets. So the feature extraction, we are starting with middle frequency vertical coefficients. And in simple terms, they're mathematical representation of sounds that help us to understand sound in a deeper level. And we also have male scale spectrogram that is based on the Fourier transform, which is a function that gets a signal in the time domain as an input and outputs its decomposition into frequencies. And this male scale is constructed such that sounds of equal distance from each other on the male scale also sound to humans as they are equals on the distance in real life from one another. So we also have the chroma feature or chromogram, which will relate the 12 different pitch classes. And it's a powerful tool for analyzing music whose pitches can be meaningfully categorized in these pitch classes and whose tuning approximates to the equal temper scale. So continue with spectral centroid, and this is a measure that is very used in digital signal processing, and it indicates where the center of mass of the spectrum is located, and it has a robust connection with the impression of brightness of a sound. And finally, with the tonus representation, which measures the tonal centroid of sound based on harmonic changes. And these features are important in the classification procedure because we need them to use our dataset with correct and incorrect click sounds. And the reason why we extracted this feature is that we need robustness against noise, its adaptability, its implementation, and containing necessary smoothing characteristics are the ideal features. So in order to certify that this feature is correct, we use a TSNE visualization. So this method consists of mapping high-dimensional state vectors onto a low-dimensional space without losing important information. And this will give us some important information on the relatedness of the components, and thus it can give us insights of the efficiency of these features to explain the correctness on the click sounds. Furthermore, it is noticeable that these classes cannot be separated by a linear classifier, thus more complex nonlinear models are required. And this was implemented in our dataset with 55,000 audio clips with the features that we already mentioned. So in the classification part, we use a machine learning model that uses backpropagation in order to adjust the weights between the connections in the network. In this case, we had three types of layers, and because it is a multi-layer perceptron, it has an input layer, hidden layers, and output layer. And in this case, we only implemented rectified linear units and logistic activation functions for the learning procedure. So we also have 25,000 samples collected, which we utilized. And we use a grateful cross-validation for the multi-layer perception architecture, deciding that 70% was going to be the training set, and the testing set was going to be the resting 30% of our data. And we also had a 213 left vector that was defined by all the extract features that represented the 0.025 second windows for the clicks. And each feature vector is pre-processed with a standard scalar function where you use the mean of the training samples, S is the standard deviation of the training samples, and C is the standardized value, as you can see on the formula. So here we have the proposed multi-layer perceptron architecture. So we have 213 units length for the input layer and one hidden layer with 256 units for neurons to the detection. And multi-layer perceptron was built with the activation function ReLU and an initial learning of 0.001, and it was trained with a stochastic gradient descent. So in order to measure the performance of our model, we tested the following in a laboratory. We tested accuracy, sensitivity, specificity, and precision, and an F1 score metrics. And as you can see, we use these formulas like a confusion matrix to test the performance of our models. So for the results in laboratory, we can see that the best configuration for these experiments was obtained with one hidden layer with 256 units and an activation function rectified linear units. According with the results, this configuration accomplished 97.35% in specificity and 95.23 if one F1 score metrics. And even though we can see that in a less complex model, like 64 and 128 units for the hidden layer, we can see better results with the logistic activation function. but this wasn't the result with 256 units. We had better results with the rectifier linear unit.